point, okay? And I said I can think of this diode as a current source, let's call it I photo, in parallel with the capacitor, let's call it CPD. Okay? The current source looks as the photodiode, and on top of that I have got a switch. This is becoming now my node N1, this is the same as this. So I make this N1 go to a very high voltage, let's call it this VRST, and I just want to know what is the voltage at this level. So now I know my voltage is falling down, that I know qualitatively. The voltage is falling down because this I photo is being integrated on this capacitor. So what will be that here? Will it fall down? High school maths, what's the current in a capacitor? So it's dependent on time. Right? There is no resistance in the circuit. Right? So dV is just going to be change in voltage. I could also call it delta V. Delta V is going to be IC times delta T by C, and delta V is whatever is the difference from here. So that will be IC divided by CPD. IC now becomes I photo times T. That's the last equation I'm working on. So I thought I was not very clear. Next one you guys are working on. So that tells me what's going to be my output current voltage here. My voltage, and that has got a kind of gain of 1. We will see what's actual effect this is going to do. My voltage is V reset minus I photo times T divided by CPD. If my T becomes fixed, if I say after this fixed time I am going to record my voltage, CPD is not changing. Diode has got a fixed capacitance. And reverse bias diode capacitance does not change any voltage. It does, but not too much. You can see my output voltage is going to be linearly dependent on my photocurrent. Isn't it? That is kind of fixed. So this minus photocurrent times something. I can call this as A plus B times my photo. Yes? It's just a linear relationship between input voltage and output. Good. In the same breath, why don't we see the eraser? There's a reason I'm making you do this maths. I said in the morning I don't like complex maths, right? But we are going to see why the image quality degrades. We've already seen what happens when high light falls. It saturates. If this voltage is very high, you just cover this whole thing. If this voltage is very low, it won't have changed by a high amount of time for me to measure. It has changed, but it will be very low amount of time. That only tells me what's the lowest current, what's the highest current I can measure. Good. Now, we are also reading this thing out. Okay? We are reading this thing through this source follower and the switch. The source follower needs to be biased somehow. The bane of existence of all second year bachelor student is what the hell is biasing. It took me another 2 years of research to understand it fully. Why do we bias anything? One of the reasons, can I take a quick break? So those who are teaching, you guys are teaching there, right? What do you teach first, BJT or MOSFET? In Warangal, what do they teach first, BJT or MOSFET? Still they are teaching BJT first. Muralidhar sir?
Yeah.
The quickest way to annoy a bachelor student is to teach him bipolar BJT's biasing circuit and quiescent point. No one understands that easily. Agreed? None of the textbooks are very nice, got very nice descriptors. They just assume you know things. I mean, whenever you do the emitter bias, you say, assume there is 1 volt and the emitter applied and there is 0.2 volt drawing across collector and emitter. No one ever understands why, at least I never understood why it is done. Nobody in my batch did. So what I do is I do exactly the opposite. I don't teach BJT at all. And there is a big advice I will give to all of the people teaching electronics engineering. Stop freaking teaching 18th century technology. BJTs are useful, but their market share is very small. They are used in high-speed circuits. So use BJT after you have done MOSFETs. So start with MOSFETs. Let life be easy for your students. They understand MOSFETs easily because they're fairly simple circuit. Right? It's on or off kind of thing. And then go to BJT. And this is what trick I learned while I was teaching in Oxford. My predecessors, they had done this many, many years ago. They always started with MOSFET in first year of engineering. Even before we do diodes, we start with MOSFET. They're much easier to understand. So with that logic, I need to bias it. So let's apply a current source at this point. Let's call this I bias. So this is the current which will flow through here. Okay? This is the voltage I said will be appearing at this point. That is just a switch. So I'm kind of going, it's going to add just a resistive value. So I'm going to neglect its contribution for the time being. The only thing which I have been left is this M2. So I know this voltage. I now need to know what's going to be my this voltage. Okay? So it's a source follower circuit. Let's see how many of you remember that calculation. So tell me what's this voltage going to be. So this I have already got. I know base current is flowing through this. I need to know that one here. If anyone needs a hint, I will be happy to provide. You need a hint. So what's the science saying here? Source follower transistor is operating in active region of operation. So we don't need to worry about linear or cutoff region. The current equation for a transistor in active region of operation is I drain to source is beta over 2. Let's not go the KW, the more complex one. Let's take our line simple. Beta over 2 divided multiplied by? Now you know why I say this is simple. That equation everybody understands. It's a simple equation. This is the threshold voltage of that transistor. Constant. Beta. Constant. The transistor is not changing, so its beta is not changing. Right? What's the gate voltage here? So what's the drain to source voltage? I am feeding that drain to source voltage. Right? So I'm doing the reverse this time. Rather than measuring voltage, rather than measuring current, I'm measuring voltage. So I give my I beta. So that is already known. So that is my that is my biasing voltage. By forcing a volt current, I'm forcing the transistor to operate in saturation region. That's my biasing. Done. Let's start calling it beta 2 by 2 because beta 2 is the beta 2 stands for beta of transistor M2. What's the gate voltage? VN1. That's the gate voltage. What's source voltage? That is kind of connected to my output. There's just a switch which is on right now. So if it is on, it's just a short circuit. That is my output. That becomes my V output minus VT2 squared. Now I can get a derivation of V output. That you should be able to do. Do it. I'm making you do for a very simple reason. You will appreciate its beauty in a minute. So please bear it with me and So if you put all of this, so first rearrange this so that you get an expression which says V out is equal to something, and then replace Vn1 with that thing here. Which I can force them to sing. So nowadays it was Tuniga Tuniga. I never understood the song. Then that and Anagarana Akasham Nundi. I don't understand, but I know the lyrics because every time I went to eat in the hostel messes, that's the same song they played. So if you hear the song so many times, you know the lyrics by heart. Good. But you can see it's not very difficult. You can rearrange the equations. See, not only I'm making you work, I'm making the poor cameraman work as well. Or else he could have just pointed at one location and then gone home. But now he has to keep on rotating with me. I'm sure the new teaching students get angry, right? All those who think they have got a paper and they have got this really small notebook, bring the big notebook because we're doing equations. Equations run longer than 1 pages. And I will make you love equations for a change, I promise you that. We don't do equations just throwing out. Whatever you will do, you will like it. What I wanted you to do, you would have got something like this. You would have got V output is equal to Vn1 minus Vth, Vt2 minus
2id by square root of 2id by beta.
I'm going to delete this for the time being. Minus IPHT by CPT. Okay? That's the equation all of you have got?
Yes.
Now something interesting is there to see. So what do we do in electronics when we start having a longer equation? You know, one of these two things we do. Either we start ignoring terms, we do that, right? We make to our students also, here's a long equation, then this, you can ignore. Or we start clubbing them together. I'm not going to ignore anything here till now. I've already ignored quite a lot by using that simple equation of transistor. The whole complex equation should have had more terms in it. But I do know this is constant. If I'm feeding a constant I beta, I bias, and beta is constant, so this is kind of constant as well. So these two are going to form a constant. CPD is constant. Time t if I keep constant for all this thing. And that is also kind of going to apply the same VDD to everyone. So I can still write this as A plus B times I photo. And just like a political party person who joins one political party and as soon as he or she doesn't get a ticket, joins the next political party, I'm going to change my words as well. Just now I said these are constant, and I'm going to say none of them are constant. So this guy is gone completely mad. At one point of time, I really wanted to stand in political elections because I thought that would be really fun. You can say whatever the hell you want, and then people will fall for it. So yes, these numbers are constant. Vt and beta are constant. But what is our aim in making pixels? To make them as many as possible. That's not what my customer wanted. Which means I need to make each pixel as small as possible. The size of the array cannot become bigger, because that is dependent on the lens. How much can the lens focus? So the size of the sensor is the same. I want more pixels in it. I want to make each pixel small. Agreed? In order to make each pixel small, and inside the pixel, what do I want to be the biggest? The one which is capturing light. Remember, it's a 2D structure, so diode, transistors all have to, which is the only thing which is capturing light there. Diode. So I want my diode to be as big as possible. Okay? Actually, we have got a number which basically tells the ratio of the diode versus the total ratio of the pixel. This is called fill factor. What percentage of your pixel is actually optically sensitive? Because those transistors, the source follower switch, they are not capturing light. We have to shield them because each transistor is phototransistor. So basically provide a metal shield to stop them from capturing light. So I want my diode to be as big as possible and my pixels to be as small as possible. The only way to do that is to make my transistors as small as possible. Now, there is a rule of the game that no two transistors are exactly the same. The smaller you make them, more is their variability. Some of you who have done electronics courses might have done things like Monte Carlo simulation. To simulate the same circuit many times, to simulate the effect of mismatch and variability. We will do that later on. But for the time being, it's safe to assume that two transistors are not going to be alike. And when we say they are not going to be alike, it means that their beta and Vt is not going to be same. Which means, for the same amount of light falling on two different pixels, the output of each pixel is going to be different. That's not a nice thing. So IPH remains same. Because of these things, I'm going to get a different output. But this output is not going to change with time. It's because once my transistor's threshold is different, it's being done at the manufacturing time. It doesn't change with time. It does, but over many years of operation. Okay? So I'm going to inherently get a noise in each one of my pixel response. A is not going to be fixed, B is not going to be fixed. This noise is called the fixed pattern noise. It appears as if a fixed pattern has been imposed onto my image. And I'll show you an example of fixed pattern noise just in a minute. Now that was the pixel level. Now remember, I also told you at the column I need to select one column at a time. Okay, before I continue, it's already 5 o'clock. What time do you guys want me to stop? Is somebody came up with 6?
Yeah. Maybe it's already 5. Another 5-10 minutes.
Another 5-10 minutes? Those without family will say 12 o'clock midnight. Those with family, if they go later, their wives and children will have nice words to say. So on the column side, you could have a similar kind of source follower selector as well. So the bottom line, our pixel looks something like this. Now we'll bring it down a bit. So that becomes my pixel. This has got 3 transistors and a diode. On the bottom I have got a column source follower bias. The bias could be a current mirror, or it could just be, if you can push it a bit up. and then I can have the output of the whole image. I'm not spending too much time in the column circuit because that's not how we design column circuits anymore. Now we just put an ADC in each column. Okay? But had we designed it like this in analog fashion, each one of these are also having a different VT and beta. So each transistor introduces a new kind of noise to it. As a result, this is what we get. So if this was my true image, what I actually capture is this. Now you know when I asked you about if you ever get drunk, what do you see? So if some of you do take up my offer and decide to consume a heavy amount, alcohol is not banned in this state, right?
No,
Not yet. Some states have alcohol banning. If I say this, I can go to jail. And one thing I don't want to enjoy is in prisons. I've already been in RC Varanga for 4 years. Don't want more. So an image is captured like this, and you can see there are many ways we call this noise. One is to see there's a pattern on it. Right? There's a straight line things. That pattern remains the same. We have to correct for that noise. It's not temporal noise, it's not changing with time, and that's why it's called a fixed pattern noise. And B, it reduces something specifically. It has reduced the contrast of this image. Here you can see the difference between these two, and here you can't see the difference between these two. It's an image from my lab, and that's why it's a hopeless image, because that's what I could get, a Mr. Shine bottle and a white paper to show how my camera is working. So, now in the noise territory, an image produced by our camera pixel is noisy. And we need to get rid of this noise somehow. If you go into noise territory, then the question next would be, what are other kinds of noises do you know? So now we're dealing with non-temporal noise. But there's always going to be a temporal noise as well. Because we have charge falling on a capacitor, the current is moving, we're going to get noise. And we are worried because remember the amount of photocurrent we talked about? femtoamperes. We have very little photocurrent and we would like to measure every small voltage difference. So what other kind of noise do you guys know of? Sorry? I know it's 5 o'clock, I can still talk. Maybe your voice I can hear as well. But I don't know any other type of noise. So in the morning we were having that display, right? And the microphone started producing a lot of noise. I thought that was the microphone taking revenge on electrical engineering professor. The moment he said that electrical engineering got more project than electronics, the noise went brrr. So what kind of noise have you read about earlier? Thermal noise? Yes. Flicker noise? Short noise? Right? These three noises will have been covered. Trust me, all three of them are going to be. So I'll only take it we're not going to do quantitative review on this noise, but we will do a bit on what these noise sources are and then try to correct for them. So let's go backwards. Short noise. So where does short noise comes from? So you might have heard of DC short noise. This is the noise which is there in the power supply. Because when we say power supply is giving X amount of current, it means X, Y amount of electrons. But electrons are not nice people, they don't all travel together, they are like our bachelor students. They all travel in multiple directions, they all come at different times. When we say it's the number of electrons moving through a junction at one point is the current. Right? They're all not, they're moving slightly differently. That gives birth to DC short noise. We have another problem here. We have got photons falling on our pixel. Photons also do not travel together. So I said 10,000 photons are hitting, giving birth to 10,000 electrons. They're all moving with a slightly different and not fall exactly at the same time. That gives birth to photon shot noise. And that's the physical limit. I cannot make a camera which will be better than photon shot noise. But that's what light is doing. So I have photon shot noise and DC shot noise, because we also have DC voltages power supply. Fortunately, they are small enough for us to live with, but they are there. The other thing which we have is, we are not very high frequency people. I think one of you teaches RF circuits or works on RF circuits. At RF radio frequencies, you ignore flicker noise completely. As if it doesn't exist. It's 1 over F noise, the frequency is high. We are not high frequency people. What is going to be my T? Remember in these equations we had a T, transit integration time. What is that going to be for me? How many pictures do I need to take in a second? What's the worst thing which I want to do? I want to take a video. There's a video camera behind us. How many pictures is it taking in a second? How many pictures do we need to take to make fool of human eye? That's a video. 20, 24, right? Let's go with 20, it's easy to calculate. So I need to take 20 pictures per second, which means in what time I should be able to take one picture? 1 by 20, which is 50 milliseconds. So we are actually operating each pixel as 20 hertz. 20 per second. We're not very high frequency people. Overall also, the ADCs operate at 110 kilosamples per second. Again, not very high frequency. So we're going to get flicker noise in the readout as well. But the biggest killer is not that. The biggest killer is Johnson noise, as everywhere else. We get noise not during the time of capture. Remember I told you, right in the beginning we reset the circuit. Okay. So some homework assignment for those who still want to see me on a Sunday. Try to go back into your books and see what's the reset noise in a simple RC circuit. So you have a resistance and capacitance, just see the noise. If not, we will derive it tomorrow. But that's the only noise which I see. So today we saw how to make a pixel. We are done with pixel making, to be very frank. I can put you in the lab and start making the pixel. Because the design is not that very difficult when it comes. So we'll do a bit of more theory. But think of it this way. I've already told you, I need the smallest size transistor possible. So you can go in a technology, pick what is the smallest transistor you can make. Put 3 transistors together. Put your the smallest transistor together in that configuration. Put a largest diode which you can draw. I mean, you at least have to think how big your pixel has to be. Let's start with the number 10 micrometer. We can go with 1 micrometer as well, because we have 118 micrometer technology here, right?
Yes.
118 nanometer. So my transistors, the smallest which is available in this lab is 180 nanometer. So if I take 3 transistors, that's already 560 nanometers. So 1 micron pixel will be difficult to make. Let's make it 10 micrometer pixel. So 3 micrometer by 3 micrometer pixel. So I already have the transistors, and I have got to fill the rest of the area with diode. And then I have to somehow connect these two. My pixel is done. And to be very frank, that is what we are going to do. But your challenge will be to draw these lines such that we're not going to do automatic layout here. Many of the digital people or analog people use automatic layout generation. We are one of the few people who still do hand layout. Because no AI tool, no automatic layout generation tool can give you the optimum. Our optimum is diode as big as possible and transistors coupled in such format and all those wiring done properly. Once we get 1 pixel, making arrays of it, you can done very easily. So we'll still do hand layout of each layer of the transistor. And we are done from pixel making. So today we finished at the active pixel sensor. This is called an APS, active pixel sensor. In more advanced technology, we will have a 4 transistor active pixel sensor, and that is to remove noise. We have already seen our image is noisy. So we will not like to remove noise in software domain, because if it has gone all the way till there, we have already lost quite a lot of signal. So we like to remove the noise using a circuit approaches right at the pixel level. But for all practical purposes, the 3 transistor pixel will work. So whenever we start cadence, whenever I have had a look at whatever technology is there, that's what we will design. We will design a 3 transistor and diode simulated to see it works. And then the main task will be layout. How do we lay it out such that, and we will run a design challenge between you guys. Whoever gets the most optimum layout, what's the prize we should offer? Okay, so whoever gets the most optimum layout will get a sponsorship for a DART fellowship to visit my lab in Germany. So whether you get it or not, that's open, but we'll certainly sponsor you for that. Maybe we can get a silver coin. That's good enough metric. For silver coin, I would have killed 5 people when I was in a batch. So run a challenge on the smallest, most optimum pixel, but the pixel has to be DRC LBA satisfied by the end of it, and it will be a layout challenge. Okay? Good. Any other questions? Any questions for the day before we end? It's already 5:13. The professor should have always asked that question at the end of the day. By the time your brains are dead, what questions? Let me go home. What time should we start tomorrow?
So start at 10 a.m. is okay?
So we do 10 to 12 or 10 to 12:30. Okay? We break for an hour and a half. So that's 2.5 hours in the morning, and then we do 2 to 4:30 or 2 to 5. Happy? So unlike, you can suggest other timings. Okay? Well, my original plan was we do everything in the evening, 4 to 7. But Professor said, or Mudira said, that's torture. And he says that's torture, it has to be torture. Good. Thank you very much. I'll see you all tomorrow. Or some of you tomorrow.